Welcome back, everyone. So last time we had an overview on basically everything you could want for MMP, and now we're going to start MMP for surfaces and try to carry out this whole program, hopefully between today and then the 2 classes next week. So just to remind ourselves, let's start with a refresher. So if X is a smooth projective surface, then our goal is to prove the following, that there exists a sequence of birational maps that are each just the blowups of a single curve in a smooth surface. So in particular, each xi is smooth, and xi is the blowup at a point of xi plus 1, where this xm is what we'll define soon as a minimal surface, meaning that it's not a blowup of a smooth surface at a point. And then once we're done with this finite step of blowup morphisms, then we have 2 options for this xm. Either kxm is nef, and we'll see that this happens if and only if the Kodaira dimension of x is non-negative, or kxm is not nef, and this happens. So, and then in this case, xm is a Fano vibration, and this happens if and only if the Kodaira dimension of the original x is minus infinity. Okay, so that's our goal for the next few classes. And then furthermore, we want to actually understand these 2 cases better. So in the kxm nef case, we'll prove that k is actually semi-ample, which means that some large multiple is base point free, and this gives us some morphism from this minimal surface into projective space, an actual morphism, not just a birational map, or not just a rational map, I mean. And if we take its image z, then the important facts are that z is proj of the canonical ring of our original x. So in particular, the dimension of z is equal to the Kodaira dimension of x. And then we can further classify what this map phi looks like in the various cases. So in the case that the Kodaira dimension is 2, then we'll see that phi is birational. Kz is ample. In this case, we'll call z the canonical model. And we'll see that z has some mild singularities. And just as a matter of terminology, so we define this canonical model, and in this case, we'll also call xm the minimal model. And then in the Kodaira dimension 1 case, we'll see that phi is a map onto a curve, and it has genus 1 fibers. So these are the elliptic fibrations. And finally, when k is 0, well then z is just a point, so phi doesn't tell us any information, it's just the map to a point, and we'll see that this is the case when x is a k-trivial variety, which means that some multiple of the canonical bundle is actually, sorry, these both should be xm's. So this should be xm, this should be xm. And we'll see that some multiple of the canonical bundle of xm is actually linearly equivalent to 0. Okay, so that's what happens when our minimal model has an F canonical divisor. And then and of course, so this is exactly the same as having Kodaira dimension non-negative, since we can't have Kodaira dimension greater than 2. And then the last case is when the Kodaira dimension is negative infinity, i.e. when the canonical bundle of the minimal model is not an F. And in this case, we have two possibilities. Either this xm to c is a ruled surface, meaning that it's isomorphic to the projectivization of some rank 2 vector bundle over C, or xm is just P2. But in particular, in both these cases, we can characterize them as phanofibration over a curve, or a phanovariety, i.e. a phanofibration over a point. We're going to start with just some background on curves on surfaces, just to get on the same page. If you haven't seen this before, most of it is in chapter 5, section 1 of Hartshorn. And we'll see a lot of this extended to higher dimensions later in the class. So again, let's say X is a smooth projective surface. And let's say C and X is a curve. And D is a Cartier divisor. Then we can define the intersection product, D dot C, by the degree of the bundle OX of D pulled back to our curve C. So now we have some line bundle on a curve, so it has a degree. This is some integer, and that gives us this product. And then there's a few other ways to define it, but the point is, in the end, what we get is that this product extends to a unique pairing from divisors on X, cross divisors on X to Z, such that 1, and maybe we'll denote this pairing, D comma C maps to D dot C, such that 1, if D and C intersect transversely, so if they're in particular effective curves instead of just some linear combination, then the intersection product counts the number of points. Two, the product depends only on linear equivalence. So in particular, it actually descends down to a product on the Picard. Okay, so that's the first bit of structure that we'll use all the time. So I'm just going to quickly recap basically everything that we'll need for this for the proof of the above theorems. Okay, so the next thing we need is a junction. So this lets us relate the canonical divisor of our surface with the canonical divisor of curves on our surface. So in particular, if D in X is a curve, then if we take the divisor Kx plus D and restrict it to D, we get the canonical divisor of D. Or if we phrase this in terms of line bundles, if we take the line bundle omega X twisted by D and restrict it to D, then we get the line bundle omega D. We'll also need Riemann-Roch on a surface. So one way to phrase it is that the Euler characteristic of OX of D for any divisor D is 1/2 D intersected with D minus Kx plus the Euler characteristic of the structure sheaf. And recall, Euler characteristic here means the alternating sum of the ranks of the cohomology groups. And this number depends only on the surface, so it's some constant. Okay, so now we have this intersection pairing. We can also define numerical equivalence. And we'll write D is equivalent to D prime if and only if D dot C equals D prime dot C for any curve C. And if we take equivalence classes of line bundles by numerical equivalence, and then for convenience, we'll tensor this as an abelian group with R, or you could also imagine tensoring it with Q. And we'll call this N1 of X, or maybe if we put the Q there, we'll put sub Q. Okay, so basically by definition, this intersection pairing becomes a non-degenerate pairing on these vector spaces. And then an important theorem is that the dimension here is actually finite, and we'll call it the Picard rank. We also have the Hodge index theorem. And one way to phrase the Hodge index theorem is that the intersection pairing on this N1 of X, which is a real vector space, has signature 1, rho minus 1, where we have this pairing, and we can on this real vector space, so we can diagonalize it, and then the signature is the number of negative, positive, or zero eigenvalues. So here we have positive, here we have negative, and because we define this n1 of x, so it's non-degenerate, we don't have any zeros. Okay, so that's the Hodge index theorem. Okay, so now we can define the cone of curves. As the sum AI class of CI, where AI is a non-negative real number and CI is an irreducible curve. And so this notation means the numerical equivalence class. Okay, and so this is a cone in the sense of convex geometry, because if we scale anything by a non-negative real number, then we still land in any of x. And if we take sums, then we still land of any of x by definition. But the problem with this cone is that it's not necessarily closed. So in convex geometry, you really want to be working with closed cones. So we'll just define NE x bar to be the closure. This is happening in the real topology on this real vector space n1 of x. Okay, and last time we defined Neff line bundles. Let me just recall the definition very quickly. So a divisor L, or associated line bundle, is Neff if L dot C is greater than or equal to 0 for any curve C. And here, whenever I say curve rather than divisor or curve class, it means effective in that it's an actual irreducible curve inside of X. The Neff cone is the dual cone under this pairing to the cone any bar X. So it's the closed cone of divisors such that whenever you pair them with a class in any bar, then you get a non-negative number. So that'll be useful. And then we want a similar criterion for ampleness, and there are two such criteria that will be useful. So we have Kleiman's criteria, which says that L is ample if and only if L dot a curve is greater than 0 on NE bar of X. And here it's important. So of course, if L is ample, then it will be true that L dot any effective class will be greater than 0. So that tells us that L is greater than 0 on the interior. And then to actually get the converse, you really need to work with the whole closure. But then there's a different criterion. Than Kleimer's own criterion, which says that L is ample if and only if. So first we have this weaker condition that L dot C is strictly greater than 0 for effective curves. And L squared is greater than 0. So if we also impose that L squared is greater than 0, then we don't need to look at the closure, basically. Okay, and now a few facts about linear series that we'll also need, basically about how linear series behave with respect to this intersection pairing. So suppose L is semi-ample. So recall this means that D times L is base point free. So it actually gives us a morphism to projective space, though not necessarily an embedding. Then if we look at this morphism for some large enough D, so if we have a curve in the fiber of this morphism over some point, then essentially by the same type of argument as why ample divisors intersect with curves positively. So we know that this dl is going to be phi upper star of some hyperplane because we have this morphism. And so if C is in the fiber, we get that L dot C is 0. But actually, because any curve that's not in a fiber will give you an actual curve in projective space. And so the intersection product on projective space will be strictly positive. Then this is actually an if and only if for these semi-ample linear series. So a curve isn't a fiber if and only if its intersection product with L is 0. And then we can also ask about what do these curves in the fibers look like in the various cases for phi. So if phi is birational, then we actually know more if you have a curve in the fiber of this birational morphism. That implies that E squared is strictly negative. And this follows from the Hodge index theorem. And these curves are exceptional curves. So it's the definition, curves in the fibers of birational maps. And more generally, or maybe the other case, if phi maps onto a curve, and we look at some D in the fiber, then we have that D squared is less than or equal to 0. So now in this case, where it's not birational, it can be 0, but we actually also know that D squared is equal to 0 if and only if D is a multiple of a fiber. Okay, and this also is Hodge index theorem. So these will be some useful inequalities to have. So when we were motivating, let me scroll all the way back up. When we were motivating this diagram last time, what we said is basically because you have existence of these blow-up morphisms, you can't expect there to be a unique birational smooth model. And so to get a nice birational smooth model, your first attempt might be to just undo any blow-ups that you have. So we're going to start with understanding the geometry of blow-ups and when you can blow down curves to smooth surfaces. Okay, so let's say X is a smooth surface and P is a point. Then we can define this blowup as proj of this ring where m is the maximal ideal of our point. We'll call it x prime. And the morphism mu. And here are a few facts about blowups that you can find in Hartshorne. If we denote by E this exceptional divisor, then first fact is that E is actually isomorphic to P1. 2, we know it has to have negative self-intersection from the Hodge index theorem, and it has intersection -1. Or another way of saying this is that the normal bundle of E is OP1 minus 1, because if you remember, the one way to define the intersection is that we look at the O of E restricted to E and take its degree, and O of E restricted to E is the normal bundle. 3, mu is actually birational, and it's an isomorphism away from this point in this curve. 4, the Picard group of x prime is actually pick x direct sum ze. So we've just added exactly one free generator to Picard. And here, the way we identify pick x is by pullback. So in particular, and this will be important later, is that the Picard number of x prime is 1 more than the Picard number of x. And 5, we can compute the canonical bundle, how that changes. The canonical divisor of x prime is the pullback of the canonical divisor of x plus one copy of this exceptional curve E. And here, we need some adjunction plus intersection to compute this. So basically, you know that the pullback is going to be canonical plus some multiple of E because of this birationality, and then you intersect and use adjunction to compute things and see that it's exactly 1. Okay, and the rest of these just follow from writing down this project description, picking generators for the maximal ideal, and just computing what are the charts on this proj and what you get. Okay, any questions? Okay, so this gives us, this motivates the following definition. We'll call E and X a -1 curve. If E is isomorphic to P1 and E squared is -1. So basically, if it looks like the exceptional divisor, or the exceptional curve of a blowup of a smooth surface. And here's an exercise, which will come up a little later. E is a -1 curve if and only if E squared is negative and kx dot E is negative. So this gives a nice numerical characterization of -1 curves. So in particular, using these numerics, you can pick out that E has to actually be P1, and once you know it's P1, then you can see that it's that E squared is also -1, not just negative. Okay. So the main theorem for today is Castelnuovo's contraction criterion. Which basically says the only way that you have -1 curves on a surface is if you have a blowup of a smooth surface at a point and your -1 curve is the exceptional divisor. So more precisely, let's say X is a smooth projective surface. And E is a -1 curve. Then there exists a morphism from x to x1. It's proper birational. Such that mu of e is a point, x1 is smooth, and mu is the blowup of x1 at p. And so this will give us the starting point for constructing that diagram, where the sequence x1 to x2 to x3 down to this xm will be produced by this theorem. And then it also will give us a condition to know when we're done. We're done, we land on this minimal surface xm if and only if we have no -1 curves, since this theorem tells us that's the criterion for having a blowdown morphism. Okay, any questions before we start the proof? Okay, so the idea of the proof and the idea of a lot of the proofs in this subject are to construct a line bundle whose linear series is base point free and that produces the morphism you want. So that's what we were going to do. We want some divisor L such that phi L is base point free, or say is a morphism. So L is base point free, and gives us this required mu. So we want to check that it has these properties. In particular, we saw that for a base point free linear series, a curve was in the fiber if and only if it intersected this divisor in 0. So this L needs to satisfy that L dot E is 0. But because E is the only curve in the fibers of mu, because once we know it's a blowup, we know it's an isomorphism away from E, we want a divisor so that L dot E is 0 and L dot C say is not 0 for any other curves. So that we can produce a morphism where E is the only curve in the fibers. Okay, so to do this, we're going to use the fact that we're on a projective variety, so we can pick some very ample divisor. So let's say A is some very ample, and we'll see later exactly how we want to pick it. And let's suppose that A dot E is K, which since A is very ample is some positive integer. We know that E squared is -1, so if we look at A plus KE as our L, then this satisfies L dot E is 0. And it also satisfies this other condition that if we take any other curve and hit it with L, we'll get something non-zero because A dot C is non-zero. And E dot C has to be greater than or equal to 0 if C is not E itself. And so it satisfies this condition as well. Okay, so this is our candidate divisor, and we want to show that this linear series of this divisor is base point free and that it actually produces for us a blow-up morphism. And to do that, we'll actually need to induct on this coefficient K. So let's define more generally Ln to be the divisor A plus NE, where N ranges between 0 and K. Okay. So step 1, we'll prove that H1 of X, comma OX Ln is actually 0 for all n in this range. And this is an induction, so when n is 0, ln is just A itself. And here we're going to use that we're picking a positive enough very ample line bundle. So we know that by Serre vanishing for any very ample line bundle, some high enough multiple has vanishing cohomology. So let's replace A with this large enough multiple and assume, without loss of generality, that H1 x comma OX of A is 0. Okay, and now for larger n, we'll induct and use this long exact sequence. So we have a short exact sequence, 0 to OX A plus n minus 1 E, then twisting up by another copy of E. And then what happens when we restrict this to E, we get OE twisted by A plus NE. So we have this short exact sequence like this that comes from twisting up by E. So we can think of this as taking the sequence OX minus E to OX to OE, and then tensoring it with our line bundle Ln. And now if we look at the long exact sequence of cohomology here, then we get sections, sorry, not sections yet, H1, H1 of OX, let me write Ln minus 1, but that's the same as this bundle, goes to H1 OX Ln, goes to H1 OE A plus NE. By induction, we know this is 0. And now here we're going to use that E is P1. So we also know that E is P1. And so OE A plus NE, well, this has to be OP1 twisted by something. What's that something? Well, it's the degree of the line bundle. And we know what the degree of A plus NE restricted to E is, because we can intersect. This is K minus N. And we're in this range where N is between 0 and K. So K minus N is greater than or equal to 0. And so it has vanishing H1. And so by induction, that implies that this is vanishing H1. Okay, so that proves step 1, which is that H1x with coefficients in OX of Ln is 0 for any n in this range. So next, we want to use that to show that this linear series is base point free. Actually, we only need that it's base point free for n equals k, and we also need that it's base point free for n equals k minus 1. But it's true for all of them. So being base point free is the same as having empty base locus. And if you remember, the base locus is the intersection of all the divisors in our linear series. But this linear series contains divisors of the form linearly equivalent to A plus some multiple of E. So think of this as the set of divisors that are equivalent to A, that are of the form divisor equivalent to A plus n times E. That's contained in this linear series. And A is very ample. So in particular, it's base point free. So we know that the intersection of all the divisors in A is empty. And so the intersection of all the divisors in A plus NE has to, at the very least, be contained in E. because of all these divisors that move around outside of E. So it suffices to just show that there are no base points within the divisor E. And so to do that, we want to understand the restriction of our sections to E, and that's where this vanishing comes up. So we know that the restriction morphism so we know this restriction morphism is surjective. Because we showed this H1 was 0. And so to show that we have no base points on E, we want to show that for any point on E, there exists a section in here. So for all P in E, we want to show there exists a section such that S of P is not equal to 0. But we know that this restriction is surjective, so we can lift sections in here. And in here, well, we know what OE of A plus NE is. This is OP1 of K minus N, which again, this is non-negative. And so we know that on P1, O of D for any non-negative D has enough sections so that there exists a non-vanishing section at each point. And so we take that section here, let's say, SP, and by the surjectivity, we can lift it to such a section S that doesn't vanish at this point P. And so we find that there are no base points inside of E, and we already saw that there are no base points outside of E as well. So this linear series is base point free. Okay. So now we have our morphism. So now step 3, if we look at this morphism, now let's look at our final one, this one with n equals k. That's the one that is our candidate for contracting E. And let's call its image x1. Well, we built this divisor A plus KE so that E is the only curve that it intersects to be 0. So we know that phi is an isomorphism away from E, and we know that E is contained, we know that E is contracted to a point, and let's call that point P1. And now, so now there's one more claim we need, which is not totally clear, which is also that phi inverse of this point is actually E itself. And here, I guess I brushed something under the rug. A priori, all we know is that phi is a bijection away from E. It can't contract any, or at least it can't contract any curves away from E. So it's at least finite. But we also, again, look back here and see that A plus NE contains this linear series of the form divisors on our variample plus n times E. And so for any point away from E, we actually just have a variample linear series, and we know that the morphism of a variample linear series separates points and separates tangent vectors, and so that's why we get that phi is an isomorphism away from E, because it contains this subseries of the form A plus NE, which is variample away from E.
Sorry, Dory, this might be
Yeah.
a simple question, but is this also what shows that it's like a bijection as opposed to like just finite to one?
Yeah, exactly. So
Okay.
if we had started with some other base point free morphism that it wasn't very ample, then all we'd have is that phi doesn't contract any curves except for E, but it still might be finite to one.
Okay, I see. Thank you.
Yep. Okay, and then the second fact that phi of E is P1, or is just a point, came all the way back from our construction, that L dot E is 0. And this third fact that actually the scheme theoretic fiber of this point is E comes from studying the linear series, this sublinear series A plus K minus 1E plus E. So basically, let me draw a picture. So here's X. It has this curve E. That's our exceptional curve. We constructed this morphism phi to projective space. It has this image x1, and we know that phi of E is some point P1, and all of this is happening inside of some large projective space. Okay, so now we can cut out this point P1 in our large projective space. Let's forget about x1 for a second. This point P1 is the intersection of hyperplanes containing it in projective space. And if we look at these hyperplanes that contain P1 and we pull them back to X along this phi, so let's draw that in orange, because they contain P1 and the preimage of P1 contains E, then we know these pullbacks contain E. And so what are they going to look like? They're going to look like some curve plus some multiple of E. But in particular, they'll contain this sublinear series. So any divisor of this form will be the pullback of some hyperplane that contains this point P. And if we look at the divisors of this form and intersect them all, because A plus K minus 1E is base point free, that we proved in a previous step, then we know that if we pick two different divisors in this linear series, they'll look like something like this, where they'll share this component E, but the other component will intersect in some other point because the linear series A plus K minus 1E is base point free. And so to get this P1, we're taking the intersection of all these hyperplanes that contain it. And so to get its preimage, we're taking the intersection of all these divisors. And if we just look at this sublinear series and take the intersection of all these divisors, then we see that actually that's just E as a reduced curve. There can't be any extra non-reduced stuff happening because just looking at this sublinear series, we see that there's no non-reduced stuff because A plus K minus 1E is base point free, so we can move it around anywhere we want. So that gives us that the fiber is actually E as a reduced curve rather than with some non-reduced structure. And that'll be important. Okay, any questions? Okay, cool. So now we want to show that this phi is really a blowup and that x1 is smooth. Or step 4, not 5. So we might as well normalize because we know that in the end, if we end up with something smooth, it'll be normal. So we might as well take the normalization, call it x0 of this x1. And then we have a diagram. Basically, from the definition of normalization, we have a factorization like this. Let's call this map F. And this is, so normalization satisfies this universal property with respect for dominant morphisms from a normal variety. So X is smooth, so it's normal. Phi is dominant because it's birational, and so it lifts to the normalization x0. In fact, once you run through the argument, you can conclude that x1 was already normal, but we don't know that yet. And then this F satisfies these same properties, that F is an isomorphism away from E. it contracts E to a point. We'll call it P now. And F inverse of P is scheme theoretically is just E as a reduced curve. Okay, but now we have this morphism F, which is birational between normal varieties. And so this actually implies that F lower star of OX is OX0. Basically because, so it uses this F is not just birational, but it's proper and birational because all the varieties here are projective. And so basically the idea here is that this push forward is some coherent sheaf, but it's also isomorphic to O away from the 1 point P and on a normal variety that says it has to be O, essentially. Okay, so step 5, now we're going to use that this push forward of O is O to write down locally what x0 looks like around P and check that it's smooth. Because of course, x0 is smooth everywhere else because it's isomorphic to x, and x is smooth. So we just need to check around P. And for this, we're going to need to use the theorem on formal functions. And this is 3.11.1 in Hartshorne. So in this special case, at least, we want to compute the local ring of x0 at P to check that it's smooth. It suffices to complete this and compute the completed local ring to check that it's smooth. And by this equality that F lower star OX is the same as OX0, then that means that we're trying to compute the stock of this sheaf at P and it completed. And then the theorem of formal functions tells us that this is the same as the inverse limit of global sections of our sheaf upstairs, but restricted to the nth thickening of this fiber. So this En is the preimage, scheme theoretic preimage of the scheme spec OX0 mod the maximal ideal to the N. Or equivalently, we can write this as the vanishing of the ideal upstairs generated by the nth power of the maximal ideal downstairs. Okay, so theorem of formal functions tells us that we can compute this completion as this inverse limit of sections, and then by this equality, that completion is the same as the completion of the local ring of x0, and then we can just observe that it's smooth once we do this computation. And now here's where we use this important fact that the scheme theoretic fiber is actually E. In this inverse limit, we have the subschemes of the form vanishing of the ideal of E raised to the nth power. And because the scheme theoretic fiber is actually E itself and not some other non-reduced structure on E, then this inverse limit is the same as the inverse limit over the vanishing of these. So I'll write it as the inverse limit of H0x O vanishing of maximal ideal downstairs to the N is the same as the inverse limit of H0x O vanishing of just the powers of the ideal of E. And so because of that, we'll just reindex things and call these En from now on. So in general, this won't be true. These MP to the N O will cut out some non-reduced structure that maybe isn't the same as IN to the as IE to the n. But because E is actually the scheme theoretic fiber of P, in this case, that is true. Okay, so now we want to compute this inverse limit. So let's start with n equals 1, or n equals 0. Sorry, 1, sorry. Yeah, n equals 1. So at n equals 1, we just have h0 x comma OE, but this is just the same as h0 e OE, and this is just our base field, which for this class is the complex numbers, but I'll probably write k anyway. Okay, so next we want to compute the global sections for these higher thickenings, these vanishings of I to the n, and here we'll use that E is actually a -1 curve. So because E is a -1 curve, then we know that that means that the normal bundle of E is OP1 minus 1, but that implies that I mod I squared, where here I've just dropped the subscript E. This implies that I mod I squared, well, this is the conormal sheaf, so this is the dual, and this is OP1 of 1. So that's what being a -1 curve buys us. And now, because E is Cartier, because X is smooth, then we know that this I is locally generated by one element. And so we get maps, we get isomorphisms of the form I mod I squared to the n maps to I to the n mod I to the n plus 1, just given by taking f and raising it to the nth power. So the point is that because E is Cartier, these are actually isomorphisms, but now we've identified I mod I squared. So this is O P1 of 1, and so by this isomorphism, we've now identified I to the n mod I to the n plus 1. It has to be OP1 of n. And so we'll use this to build up this O of En that we need to compute. So now we have the sequence 0 goes to I to the n mod I to the n plus 1, goes to O E n plus 1, goes to O E n, goes to 0. We know that H1 of this vanishes then, because it's O of n for n positive. And so when we take global sections here, we get an exact sequence, a short exact sequence still. So we have 0 to H0 In mod In plus 1, goes to this H0 O En plus 1 we want to compute, goes to H0 On that will compute by induction, goes to 0. And now let's see what happens so we can figure out the answer. So we already said that when n is 1, then we know here we just have k. And then when n is 1, I mod I squared we said is O of 1. So what are the sections of O of 1? Well, they're linear forms x and y. So whatever this thing is, it's an extension of k by x and y. And so it has to be kxy mod xy squared, just polynomials of degree at most 1. And now we can continue building this up. So we'll say by induction, we know that, or we'll assume as our inductive hypothesis that O H0 O En is kxy mod xy to the n plus 1. Mod n, I got the indexing wrong. Then over here we'll have H0 of I to the n mod I to the n plus 1, but we said that that was just O of n on P1. So here we'll have H0 of OP1 of n, which is the same as forms of degree n. And so this extension is kxy mod xy to the n plus 1, i.e. forms of degree n plus 1, at most n plus 1. Or polynomials of degree at most n plus 1. And so putting this all together, we get that OX0 at the point completed is the inverse limit of kxy mod xy to the n over all n, which is this completed power series ring in two variables, which is the completed local ring at a smooth surface. So now we want to check that this actually is the blowup. And now we'll use the universal property of blowups. So we have this map x to x0. We know that x0 and x are smooth. We can take the blowup of x0 at p. And the universal property basically says that a map like this factors through the blowup if and only if the preimage of the subscheme we're blowing up, or the subscheme cut out by the preimage of the ideal that we're blowing up, is a Cartier divisor. But we know that's true here because the preimage of P is this E. And we get this factorization like this. We'll call it mu, and we can check that now. This has to be an isomorphism. So in the last 4 minutes, now we can give a definition. X is a minimal surface. If it contains no -1 curves. And as a corollary of Castelnuovo's theorem, we get that for any smooth projective surface, there exists a sequence of blowups which is finite, so specifically a finite sequence. Of these blowup morphisms where each xi is smooth and 3xm is minimal. And the last bit of the proof of this that we haven't seen so far. So how would you do this? You'd start with x0. You'd find a -1 curve. If you can't find a -1 curve, you're done. Then x0 is already minimal. So if it's not minimal, you find a -1 curve. You use Castelnuovo's theorem to produce a blowup. And then you want to check that you'll finish eventually, but now you use that we know the Picard numbers. So Picard number of xi is equal to the Picard number of xi plus 1, because we're adding this new exceptional curve. And so this also has to be greater than 0. And so we have to terminate eventually because we keep getting smaller and smaller Picard numbers. So eventually we'll reach some xm where we can no longer blow down a curve.